should go on mute. Please mute yourself. Right. So what we understood from the neural networks is a neural network is a layered architecture wherein you see an input layer from which the data is presented to the network. And the number of neurons in the input layer depends on how many features you have in the feature vector of every data sample that you have in your hand. And the output layer neurons depends on how many classes you have or what's your expectation is about. And the hidden layer that we decided, like probably you will go with trial and error basis on the number of neurons in the the hidden layer, or maybe based on your experience previously handling such similar problems, right? And what comes along with is the training of neural network, which is where you present the training samples with multiple, several iterations through the forward pass. And after every sample passing, you will do the back propagation to adjust the weight so that the network learns each and every sample in a best possible way. And after a number of iterations, the network becomes so efficient that the weights are tuned to work for all the data samples, right? So yes, now if you try to use a cascade of many such hidden layers instead of just a single hidden layer, and each layer is responsible for processing the data that is given to it and converting it or pushing it to a non-linear space because there is a squashing function. So if you try to bring in many such layers between the input and the output layer, okay, what you can expect is each of such layer will do the non-linear processing of the data that it receives and does the feature extraction and transformation, basically the non-linear transformation. And each successive layer uses the output from the previous layer as input, and the algorithm may be supervised or unsupervised. Supervised in the sense you keep the expectations at the output. Unsupervised is where you do not have any expectation but you just want to learn the data. Okay. And the networks are based on unsupervised learning of multiple levels of features, meaning that if you assume one layer is doing one transformation, I mean taking the input features into one nonlinear uh, transformed space, right? The subsequent layer will take the transformed data further into a newer transformation, right? So it is the next transformation that is applied on the transformed spaces already. So in a way, if you keep several such layers, at every layer, the features of the previous layer get transformed to a new space. And when you think this transformation is done, in a way that the network is trying to see the data at different perspectives. So each transformation is just that you are pushing the data from one space to a different space. In a different space, there may be some other attribute, some other hidden structure of your data, which can be opened up and visualized to the network, and the network tries to learn from that representation. Okay, so we want to achieve such several nonlinear transformations. And also you can think that because it is transformation of the transformed features, meaning that it is trying to combine the features into a higher level features. Okay, so that is achieved. And as a part of the broader machine learning field, it is trying to learn the different representations of the data and learning from multiple levels of representation that correspond to different levels of abstraction, and the levels form a hierarchy of concepts. So deep learning is nothing different from the neural network, or deep neural networks is nothing different from the neural networks that we just understood. It is just that it is an extension of the neural network with added several hidden layers between the input and output layer. And the advantage of having such several hidden layers is that the data will be transformed several times, and the transformed data will be pushed for further transformations. And in a way, it is trying to see from low level features to high level features, and all different possible ways of looking at the data, right? So it is trying to represent the data in a best possible way possible, so that your desired outputs can be achieved as a combination of all the different layers. Okay, so that's the concept behind having lot of hidden layers between the input and output. So whenever you see a neural network with at least two or more hidden layers, then you can call such a neural network as a deep neural network. So why it is deep? It is trying to go deep into the feature extraction by transforming the already transformed features to see the the different views of the data, to open up the different you know characteristics, the different attributes of the data, the different properties of the data in conjugation with other data samples. Okay, so with that motivation, if you try to see it mathematically, what a deep learning or deep neural network is, it is composition of nonlinear transformation of the data. So you know what is composition of functions? Like there is one function, on top of it, if you apply one more function, then you call it as a composite function. That means it's a function of a function, correct? And each of such function is a nonlinear function, and it is a composite nonlinear function. Okay. Right. So deep learning is a composition of non-linear transformation of the data, and why we need deep learning is to learn useful representations, that is features directly from data. So the other advantage or other requirement why we are trying to use deep learning is I want to free up the machine learning from the expertise that is required in doing feature extraction. Meaning, I want to start with the raw data. Raw data means in whatever form the data comes, I want to use that form itself and push it as input to my network and get the data represented in a best possible manner. So what do you mean by representation? Meaning it is just the features. So in the earlier simple neural networks, we understood that features is the important factor, and features were submitted by you, meaning you have done the feature extraction, and the network takes the extracted features. Meaning if it is a image problem, you may be going with several image based features. If it is a text problem, you may be going with text based features. So you do the representation first, and you push the represented data, a feature vector, to the network and ask it to train itself using those features. But I want to free up my uh, network from accepting a supervised features. Instead, I want to push the raw data, and I want to see that my network, my machine learns the features, learns the representation by doing several nonlinear transformation of the data. And the representation should be well aligned to my um, expected problem. If I'm looking at a classification problem on this particular data set, which is a image based data set, then the features that it is expected to use or create or generate, or the representation that it generates for my data, should be aligned to my classification problem. If yours is a regression problem, then the features may change. So the features that are extracted from the network, or the way the data gets represented by the network, will be uh, you know dependent on the task that you're performing. So it is now much coincident that the features are aligned to the task, whereas in the previous case, you decide the features irrespective of what task you're trying to perform. Like even if you go for image recognition, you may go with the same feature extraction. You do image classification, you extract the same features, right? Maybe that, and in some sense, sometimes you may feel that the features that I'm extracting, I'm not very sure whether I'm extracting right features for the purpose that I'm trying to build my model. So I want to see that the features or the representation of my data is, uh, you know, specifically made a tailor-made representation for my data. So that is your goal. So what are you trying to learn here in the deep learning? I mean, what the network is expected to learn? The network is expected to learn how to represent the data which is best suitable for the underlying task. Okay, so there are many varieties, can be supervised or unsupervised. So let's discuss the supervised uh, deep learning, especially the convolution neural networks today. Um, like this is how I'm trying to visualize the network's learning. I want to push in the raw data itself, meaning if it is an image problem, I want to push in the raw pixels itself as the input. I don't want to do some feature extraction like you do the feature extraction or texture based features or shape based features, right? You do a lot of several feature extraction. There are plenty of such feature extractions that you can use in images, but which feature extraction technique is best suitable for my data domain or my particular problem is not sure. They are generic feature extraction techniques. So I don't want to get into generic feature extraction to be adaptable for my specific problem. Instead, I want to see, I will start from the raw data itself and let the network decide what should be the best set of features or best possible representation of my data, which can achieve my target task. Okay, so this is called as representation learning, and having lot of hidden layers in the network will make it uh, you know a possibility that the network tries to look at the lower level features in the initial layers, and as you go through the higher layers, I mean the deeper hidden layers, because these the previous layer is taken as the input for this layer. So this is studying the combination of these features. So you can think that this initial layer may be just simply looking at some edges. Maybe this is trying to do some composition of edges, and it is trying to do some more, abstract representation of those composite edges. And here at the deeper most layer, you may be expecting the hidden layer to represent the object at its best possible abstraction, so that the abstracted high level feature is used for the classification layer at the end. Hope you understood how this hierarchical way of learning the representation is helping the network to achieve the desired task. And this is trying to learn this representation, keeping your desired outcomes as the deciding factors. So the representation is decided based on your task, based on your data. It is not a generic representation like a color based or texture based or edge based or shape based, whatever it is. So it is purely, you know, dependent on the problem. So if you do not have such a specific problem in hand, like you want to do the classification or kind of, then you may be thinking of going to unsupervised. Then also you can keep the layers and input the data and ask it to learn the different representation so that it is unsupervised without any expectations at the end. Okay, such a learning is called as unsupervised learning, but having supervised learning will make it you know more efficient, so that the network learns keeping in the target, uh, the desired target in its core of the representation learning. But several times you may need to go with unsupervised learning also, where you do not have the labels associated to every training sample, which is a kind of like clustering example. Then you probably go with without having any dedicated targets, right? In both the cases, you can think of having a stacked up layers of hidden layers in the neural network to achieve this abstraction and high level feature representation learning possible. So it is expected that the natural progression from low level to high level feature, such as seen in the animal, this natural complexity, and easier to monitor what is being learned to guide the machine to better spaces. It is not just an imagination or just a hypothetical way of understanding it. It is actually possible to visualize what the neural network is learning at which layer by visualizing the feature maps of every hidden layer. Okay, probably in one of my demos I'll show you this, what I mean, where the neural network is focusing, what the feature, what the network is trying to learn by trying to visualize the network's learning feature maps. Okay, so as another example, if you see, like if it is some face recognition problem, so it may start with some edges initially, then gradually it may move to the object, the different face parts, and at the highest level of abstraction, it may be representing the faces. So similarly, cars, elephants, chairs. So these are actually the pictures extracted from the different layers. Means the feature maps that are extracted from different layers of a network that is trained for respective purpose. Okay, so with that motivation behind, if I try to recollect the supervised learning problem, so you got a sample and you got a expected output, like you are posing in one training example to the net, I mean to your learning algorithm, and you have kept the label. Say you are pushing in face and saying that it is face. You are pushing in car and saying that it is a car. So it's a classification problem between face, car, say elephant. So there are a lot of examples. I mean, different categories present in your problem. You push several face samples and keep the face as the target category. Similarly for other categories. So what is expected out of this black box is to uh, do the feature extraction and representation and then learning and then classification. So all this is expected out of this black box. Okay, so example has a here, like in a classification problem, you may push the samples and keep a target label or the category label as expected output. In problems like image denoising, your input is a noisy image and output is a noiseless image. So this falls under the regression kind of problems. Okay. And sometimes, like if you have a problem like OCR, wherein this is a a scanned image having your characters, and you want to generate the corresponding category labels for each character present here. So it is a structured prediction problem. So all such are the supervised learning problems, but basically every supervised learning problem will require this algorithm to come out to this particular output requirement. Okay. So how about the supervised deep learning? If you try to look, the simple single black box will be split into lot of several smaller black boxes. Okay, each black box is taking the processed data from the previous black box and finally trying to achieve your desired output. Okay, so deep learning is about the learning feature representation in a compositional manner. But why should we learn features? Like if you try to imagine the black box in the traditional image classification or image recognition problem, you do pre-processing, you define what are the pre-processing steps, right? You write some image enhancement, denoising, all those steps first. Then you write some feature extraction uh, steps, meaning you decide what should be the features, like the gradient based or point based features or texture based features. So you decide them. Then you probably may do some more post processing, like transformations you do after feature extraction, right? Maybe you may do PCA right after this, and then push it to a classifier that you decide, like a support vector machine, maybe the tree based classifiers, whatever. So for so many traditional classification techniques that you have come across, you will decide one of them and use it, or maybe combination of them. But each of this is hand engineered, meaning the expert decided what should be my pre-processing, what should be my feature extraction, what should be my post-processing, what should be my classifier. I want to avoid all this because it is these stuff are most critical for the accuracy, and definitely it is most time consuming in development because whatever may be your expertise, you may not be able to choose best feature extraction, best post processing, best classifier in one go for any given problem. You might need to do several experiments and several analysis of several set of combinations of such before selecting the best one. So which is the best requires a lot of analysis. And what next, like once you achieve some level of accuracy, how to go about further. So can you keep tracking or cracking better features? So instead, let us try to learn feature representation directly from the data itself, not hand engineered. So ultimately the concept of deep learning is to learn both features and classifier together. Have you asked your neural network to use SVM or a nearest neighbor, right? Or a decision tree? No, you have not asked any particular classifier to be used, or you are not going to ask any feature representation to be used. I want my network to learn both features and classifiers together. And when I say together, both will be learned, and these features will be more tailor made for this classifier, and this classifier is more tailor made what based on what features, and these two are tailor made to your target task. So I want to learn an end-to-end recognition system. Just I have my data as input, I have my outputs expected, and everything else is I don't want to give anything from my side which is expert made or hand engineered. I want everything to be learned by the system. So a non-linear mapping that takes raw pixel, in the case of image problem, that takes raw pixels to labels. So input is raw pixel. You convert the you know, whenever you read in an image, it is a collection of pixels. You vectorize the pixels, push it as the input, and keep the labels as targets, and ask the network to train, adjust the weights, learn the features, do whatever you want. Ultimately try to generate these labels. So how can we build such a highly non-linear system? It is not a simple non-linear system at one level. It is trying to learn from the raw data all the way till the labels. So what is that mapping that is existing inherently, and what is the nature of that mapping should be learned? So the answer is by combining simple building blocks. So I want a highly nonlinear system, but the answer is it is possible by combining several simple building blocks to achieve any complex nonlinear system. Why? You know that each hidden layer has several neurons, and what each neuron is doing, it is just accepting some input and weights, performing summation and doing squashing and forwarding the result to the next neuron. And that's that simple neuron functionality, together with thousands and millions of neurons connected, is trying to achieve a very big non-linear complex system. So one example is, so you try to build one function which is very complicated enough by combining all pieces, whereas other proposal is you go from lower level of complexity to higher level of complexity, and at each level see that the transformation is happening every simple non-linear transformation. So two simple non-linear transformation is nothing but one big complex nonlinear transformation. So when you apply another simple nonlinear transformation on this, it becomes even more complex. So by the time you reach here, right, it is a very complicated nonlinear function that is achieved. But if you look at individually, they are all simple nonlinear functions. So that is the idea. And if you see from mathematically, it is instead of um, having one complicated function, I want to do a composition of several simple uh, nonlinear function. Okay. So composition is at the core of deep learning methods, and each simple function will have parameters subjected to learning. So let's try to understand how that happens and what are all the learnings and how the neural network training changes from what we have understood in the simple neural network concept to this deep neural network. But the foundational aspects remain same, and depending on the application and the data, some of the things will change, which we'll try to address. So as an example, if you try to perform a classification of different objects like car, so you push in the draw image pixels of car and the category label car, and you ask the network to try to represent and learn and finally come out with a best possible set of weights, which when I push this image or similar image, it has to decide that it is a car. Okay, and each box you can map it to one unit of the network or one layer of the network, and each layer will have its own trainable parameters, because you start with some random uh, weights, and gradually those random weights should be fine tuned, so that they will achieve your desired task, right? Is then again another way of visually understanding how the deep learning is working. So starting from raw pixel, it may take like one linear transformation from pixel to the hidden layer will take the pixel combination to achieve a one non-linearity. Thereby, it is trying to study some basic edges. Okay, different types of edges, and then the next layer which takes this as input will try to learn the combination of edges possibly to generate some object parts from the edges. So I may be skipping some layers here. So it may not be true that only 3 layers are sufficient for this particular problem. There may be several such in between layers, okay, to achieve that. So ultimately, the deep learning based networks try to learn from raw data the ultimate requirement of your task. Okay. So again, the concept of neural network training comes back, like you have the sample that is going all the way forward to the from the first layer to the last layer. In between, there could be several hidden layers. Ultimately, it is generating one final value as output, and you check that value with the desired output. The difference, right, will give you the error. Now you try to back propagate that error all the way back to the initial layer, and in your journey of going back from last layer to first layer, try to adjust the weights based on this error with the learning function that we just understood previously. Maybe some differences, some variants of such learning functions are available today. So there are several possibilities for every thing that you decide. Those are called as hyperparameters of your neural network. Okay. So the neural network training now is again back to the same neural network training, even in the case of deep learning. Start from initial layer, go forward all the way till the last layer. Once you generate the output, you compare it with the desired output and compute the error or loss and try to back propagate that loss all the way back to the initial layer, and this back propagation is driven by this learning rule or learning function, which we call it as a gradient based learning function. Earlier we saw that I just used the difference of the expected and desired output, but now I'm trying to use some function that's a differentiation function, or you can call it as a gradient function. What is gradient? Gradient is basically a derivative, correct? So L is here in my case the loss or the error or the difference between your desired and actual output, and W is the weight which you are trying to update. So my weight that I'm trying to update will be updated as a factor of its gradient with respect to the loss. So what is the effect, or what is the effect of, or what is the change that I see in the loss if I do a small change in the W? Correct. So differentiation says what will be the change of one function. Loss is a function for you. So what is the change in the loss function when you change a small amount of the dependent value, that is W? So keep that change and take the factor of that change, update your weight, so that uh, the the loss, overall loss, gradually comes down. Okay. So, and one more aspect that you have to understand is the loss updation or the weight updation will not happen in the deep learning. The weight updation will not happen at every forward pass of a sample. Instead, you pass several mini batches, means you divide the training data into small batches. Just because if you try to adjust the weight after every sample is forwarded, it becomes like very unstable, meaning your weights will get fluctuated a lot after every time you pass in a vector and get it updated. Instead, divide the data into several small batches of randomly chosen samples. Push one batch, means do forward pass for the entire batch, and try to update the weights at after a batch, so that the deviations or the fluctuations are less and the training will be smoother. Okay. So that is called as batch based learning. And then this batch size, I mean how many samples should be passed in one forward pass, is also going to be a hyperparameter. Okay, meaning you have to decide it. Say you may decide to go with a batch size of generally, like the batch size are generally are the powers of 2, like 2 4 8 16 32 64 and so on, depending on your computational power, because the implementation of the forward pass is made very optimized, that it will not take one sample at a time. Instead, entire batch will be pushed once by using the matrix multiplication concept, the several matrix composition concept. So if you are pushing 100 samples and each sample is having some 1,000 features, then it becomes 100 by 1,000 bigger matrix that goes in as a one batch. So the computation power should also be similarly uh, good. So depending on how much is your computational power, you decide the batch size, and also based on your feature dimension. I mean, if your image is of size say 256 by 256, if you convert it into a vector, that becomes a very big feature vector. So you will decide the batch size depending on that requirement. Okay, so probably you'll come to know when I take you into the demos. But the crux is the same concept that we have understood in the neural network. You forward the samples, update the weights in the backward propagation, but during the updation, instead of using simple difference of the output and the generated output, you use a loss function and you use gradient computation. Gradient is nothing but a simple differentiation or a partial derivative of this loss function with respect to one of the factors. Okay, it's a partial derivative. And this concept is driven by called a concept called the optimization technique called as gradient descent. So your actual requirement is to reach to a lower error. Okay, and this is the W that you're trying to adjust. Initially you chose some random weight that may be somewhere here, okay, or maybe somewhere here. So the random weight that you have initialized for that particular connection, but that random weight is not optimal to lead you to the lower error. So this is the global minima that you want to achieve, meaning your weight should be gradually adjusted from here till here. You cannot go in one step. That will take several steps to go forward, one step at a time from this peak to this, because if you take larger steps, probably it may reach to here. Then again, if you continue to adjust the weight, it may go again to the top. So you may be missing this lower minima if you take larger steps. That's the reason why this factor n or eta, or we call it as learning rate, matters. So keep the learning rate small so that the ball or your weight gradually updates in a smaller steps, continuing towards the lower or the optimal minimum of your error. And don't keep it so small that you will require thousands of iterations, and don't keep it so big that you will always be deflecting from deflecting out of the minima. So you may come over here because of your learning rate is bit high. Instead of going here, it may just go to here. Then again you try to adjust, it will come back here, it will come back. So you'll always be playing in these 2 points. It will never go to the minima. So try to keep it as small as uh, the one that will help you to reach to this global minima. Okay, so this concept is called as gradient descent, and this is your error function or the loss function. Okay, so loss function, you are trying to differentiate this loss function with respect to this weight, and that is called as gradient. And if the gradient is positive, you move, you know, you increase the weight. If the gradient is negative, meaning your error is here because of the weight, then you have to reduce the weight. That means you will subtract the weight from the gradient. So your gradient direction decides whether to increase the weight or decrease the weight, and your gradient value decides how much should it be increased along with the learning rate factor. Okay, so this is called as gradient descent technique. Probably you can dig down further from this philosophical understanding of this concept. And there are a lot of variants, and even today this gradient descent is the core of all the deep learning techniques, but with lot of variants. Okay, there's a stochastic gradient descent, and this is called as optimizer in the deep learning. So you will choose adaptive gradient descent, or SGD is called as stochastic gradient descent, and there is ADAM, which is adaptive momentum based. There is a momentum based gradient descent. So a lot of variants are available today. So I think with this motivation and the philosophical understanding, you can go ahead and try to learn more about the different optimization techniques available in the current state of art. So, so that is how the deep neural network training happens. And when I say uh, I'm going to take up image as an example to learn the computer vision
Sir,
in deep
can you
learning.
please explain
Yes.
how by taking this small error rate we can conclude to the global minimum, and how are we going to avoid the local minimum?
Yeah. So as I said, basically this is one backward propagation, right? And it is not that this is the only weight that is affecting your or generating this loss. So this loss, so if you see a neural network, a deep neural network, so the deep neural network is based on the composition of several such layers, and each layer has several weights, and each weight is contributing to your final loss. So you want to adjust each weight, and when you say that there is a function which is being driven by a lot of, what you call it as, a lot of other dependent factors like weights in this case. So you have to adjust that loss function, or you have to adjust those weights so that you reach to the core of the or the local global minimum of the loss function. So when I say that, you have to adjust each and every weight with respect to the loss that you have. Meaning you have to first understand what is the effect of this weight for this loss function, that you understand from the gradient computation. So if the gradient is high, then this weight is having big contribution for the loss function, and this weight needs to be changed to a drastic extent. And since it is only one back propagation for one mini batch, we do not want to make it completely zero here by adjusting the weight exactly to the gradient value, because that will make it uh, you know overfitted to that weight, and we want to see that the other weights are also responsible for learning. So that is the reason why you take a small proportion of it for this mini batch, and gradually after every mini batch forward propagation and back propagation, the weight at each and every layer will get updated. So all in all, in one back propagation, say if you have 1,000 weights of all of the entire network, and all the 1,000 weights updation based on the gradient will lead to a new loss. That loss will be lower than the previous loss. So you try to reduce the loss in one back propagation. Again, you forward pass, again there will be a loss, you try to reduce the loss. So this will go go on and on several times for every batches. Say you have 100,000 samples. You divided them into batches of 16 samples. Then you got some batches. You pass one batch after the other, do the weight updation after every batch. Then you have one forward pass completed. Means entire training data is shown to the network once. Again, there is one more. So this is called as epoch in the concept of deep learning. So one epoch is nothing but showing your entire training data one time to your network. So there is a weight adjustment. Now again you go to one more epoch or one more iteration where again you do this batch processing, show the network the samples again, weights will again get updated. So after every epoch, the weights will be adjusted in such a way that the overall loss is reduced at every iteration. Okay, and at every iteration when the overall loss is reduced, you see that. And in actual case, this is not a simple two-dimensional function. It is a very complicated n-dimensional, loss function that you will be working with. So because it is going to be affected by so many weights, this will be very complicated loss function. So we are just trying to visualize with respect to one weight, and that's the reason you see a simple curve like this. So at every backward propagation, the corresponding weight gets updated to some extent so that it is moving towards the local minimum. So if this is the weight, say for example 3, I make it 3.5 after my back propagation. Looking at the gradient is positive, and I decide a portion of that gradient, say zero point 0.5, so that weight 3 becomes 3.5 after one back propagation. A specific weight I'm telling about. Next again, one more batch gets propagated, and this weight may become further improved. Okay. So likewise, in after every batch, after every epoch, the weight will gradually move towards the local minimum. Okay. And when you reach this local minimum for every weight, then that is the end of your training. Okay. So after all the weights are tuned so that they are helping your loss to go to the local minima, your network training will end, meaning that the overall error will be less. So when the overall error will come down to a smaller extent possible, it is when all the weights are tuned so that they are uh, giving you least possible error. So then the overall error of all the weights is going to be very small. So you keep a threshold. I want to uh, go on and on um, doing the training. Like you said, 100 epochs means 100 iterations of your training data. So after every iteration, you see that the loss is reducing and the accuracy will be increasing. And one fine iteration means in one fine epoch, the loss will be very minimum. You may stop at that point and take the weights that are adjusted at that particular step and stop your training. Or I mean, you may take the snapshots of different steps, I mean different epochs, and then decide whichever epoch which has least possible error. So that is how it is possible. So I will show you a couple of examples in that later. Okay. So that's the training and back propagation of neural networks weight adjustment process. So specifically because we are trying to discuss about the images, so how do you push an image as input to your neural network is you convert um, the image into one single feature vector. Okay. And if you see that if you have converted image into a feature vector, so this becomes from two dimensional, it gets converted into a one dimensional data. And because you know that in neural network, if you consider one specific layer, means just a layer after the input layer, a neuron, what we have understood is a neuron in the hidden layer will be connected to all the other neurons in the previous layer, correct? So that is how the combination connection is. Because image is so big, generally we handle high definition images today, meaning that there'll be around 1000 by 1000 at least. Then 1000 by 1000 is 10,000 dimensional feature vector. So every neuron is having 10,000 connections just because if your image size is 1000 by 1000. But today we are seeing very high definition images which can go up to 10,000 and 10,000 dimensions are also possible. So one thing that you have to understand is if the number of connections are high, or if the input dimension is high, and directly the input dimension decides the number of connections, and the number of connections decide the computational burden, correct? For every connection there is a computation happening, so this value will have one weight and there is a computation. This weight will be multiplied, and again every other such connection will have such multiplications followed by addition at this neuron. Again this neuron will have all the connections similar to this neuron will have all the connections similar to this. Okay, so if you assume an image with 1000 by 1000 size, and if you say there are 1 million hidden units, then this will convert to 1 billion parameters at one particular layer itself. So 1 billion parameters means it is a very big computation that is required, and definitely it becomes like unimaginable, and your computational resources may not be sufficient for this purpose. So the computational burden increases as your input size and your hidden layers and the number of neurons in the hidden layers increase. So you have to either resize the image and keep the smaller number of hidden layers and keep lesser hidden units, I mean lesser neurons in each hidden layer, so that you can accommodate the network training in your computational resource. Otherwise it is not possible. So that is one aspect of it. On the other hand, can I still go with a bigger hidden layer and each hidden layer having lot of neurons, but try to reduce the connections? Okay, so you can do so if the input is image, because if you try to imagine a image as your input, the data is not connected at every pixel. If you see, so there is spatial correlation at every local patches in the image. So this, for example, this image having this person, um, you see that the pixels corresponding to eye are correlated. I mean, they are interconnected so that you decide that this is a eye. But this pixel, which is present at the eye region, is not at all related to a pixel which is present here, which is present here. So there is no meaning in connecting a neuron, these pixels along with these pixels, correct, to study the relationship, to come out with a summing and squashing. I don't want this neuron to look at any other pixels apart from this region. So there is a spatial correlation which is local, and hence better to put my computational resources in increasing the layers, in increasing the neurons, rather than unnecessarily connecting all the pixels to all the neurons. So that is where the spatially correlated neural network comes into picture, which is the convolutional neural network. Okay, so this is where if you try to connect every pixel to every neuron, this is how it looks like. So assume you have a 32 by 32 image with three channels like RGB. If you convert this into a one-dimensional vector, because you have to pass it to a input layer. So if you convert it into one-dimensional vector, it gets converted into 3072 by one single dimensional vector. So if this is your input layer, meaning your input layer has 3072 neurons, if all of them are connected to a hidden layer which is having 10 neurons, then how many weights are there? 3032 by 10, correct? For one neuron. Again, one more neuron, again those 10 into 3072 connections. So each connection means each a computation increases, right? So a fully connected layer is nothing but the whatever we have seen and understood in the introduction of neural networks. A layer and a next layer is connected fully. Means every neuron in the previous layer is connected to every other neuron. But in the case of images, we do not need it if you try to understand the image perception. because they are not related at every pixel, they are related locally, and those local connections are, you know, getting combined at higher level of abstractions to form this object. Correct? So just remember this fully connected layer, which will come back again. Uh, but here we want to avoid this fully connected layer in the case of image. And how to avoid? You reduce the connections to local regions. You present this neuron only this patch, and this neuron only this patch, and hence, so if you have 1000 by 1000 image, and if you have 1 million hidden units in a layer, and if you keep a patch size or a filter size of 10 by 10, so look at only 10 by 10 region of the image and connect those 10 by 10, meaning 10 by 10 is 100, so 100 neurons will be connected to one neuron, and hence the number of connections reduce. So assume connecting 10,000. How many it is? 1000 by 1000 is, so 1 followed by 6 zeros. Connecting so many neurons to one neuron is a very big number. Instead, connect only 100 neurons to one neuron. That's a smaller. So the number of parameters, meaning each connection will have one weight to be learned. Correct? So if you reduce the number of connections, you are reducing the number of weights, and hence each the number of parameters that you want to learn are reduced. So from 1 billion parameters with fully connected layer, you are now reducing with the spatial, uh, you know, patch based connection, you are reducing it to 10 million. There is a very drastic, and if you reduce this size, it will further reduce. If you increase it, it will increase. Okay, so you choose a proper patch size, so as to make sure that you are not missing a proper local region of the image which is having a prominent object part, and don't make it so big that it is covering several parts. So then comes another hyperparameter, that is the filter size. This 10 by 10 is again should be decided by you. Okay, but again based on the, several applications, we have lot of recommendations from the, research community and the application domains on what should be the filter size at what layer and on what type of data, right? So such recommendations are very helpful for you when you decide, when you try to decide so many hyperparameters. Okay, weights anyway are not under your control, they will be learned by the network, but the number of connections will be decided by you based on this patch size. But this patch size requires some closer look at the domain and the image size, everything. Okay, great then. So hope you understood why we want to shift from fully connected to a spatially connected network in the case of images, so that we use the patch wise. And one more level of reduction in the terms of number of parameters is we want to keep same parameters for this patch. So let this patch be used here, 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 everywhere, but I want to use same weights, same parameters for that patch wherever it goes and tries to look at. So this is small region, assume is a small window. You you use that window to look at the entire image from left to right, top to bottom, and at every region that I'm looking, I keep the parameter fixed. Fixed in the sense there's the same weight, but that weight will be adjusted over the training. I want to fix the weight, and hence for a patch you are having a same parameters all across the different location, and hence you are trying to reuse the same kernel. Now this patch or a filter, what I called you, is called as a kernel, which is transforming this particular region of the image into a representation. Okay, what is kernel ultimately is something like a nonlinear function which is transforming the data into features. Okay, so uh, those are the, building blocks that you need to understand going forward to the convolutional neural networks. So with this, I mean, convolutional networks are not simply taken up for images without any strong reasoning. These are the strong reasoning. I want to reduce the computational burden, but not at the cost of losing information, not at the cost of accuracy. So I take a deeper look at the data. My data is image. It has spatial correlation, not the entire image correlation. Or not all pixels are related. So they are related only locally. Then I came across with a patch concept, and I wanted to keep the number of parameters less, and I reduced, I mean, I try to reuse the same features at every uh, region, that the same patch or the same kernel or the filter you can, and then these are the different nomenclatures that this is used, but you can invariably use it as filters or kernels. That's one. Now, is it only one kernel that is sufficient? No, I want to look at this image from different windows. Each window gives me one perception of the image. So meaning each filter will give you a different feature extracted, different, the appearance of your image. It will try to extract a different feature altogether, meaning that I want to use several such filters for my image. Let's say learn from multiple filters so that I can learn multiple features and I can represent my image in a best possible way. So let's say for my 1000 by 1000 image, let me decide I go with 100 filters and each filter of size 10 by 10. And there is some restriction. You cannot have varying sized filters. It should be standard, and this will lead to only 10,000 parameters in that case. Okay. Yeah. Is there any clarification on this? Maybe let's go further to understand the convolution concept in a detailed factor. So assume this is your image 32 by 32 by 3. 3 is the number of channels, and I keep a filter, say 5 by 5 size, and this 3 is, whenever your input is having 3 channels, so you're expected to have 3 in the filter also. So this is automatically decided by how many channels are present in your data that is applied with this filter. Okay. And the operation that this filter does on this image, meaning this filter will be used to look at the several parts of the image in a very defined way, meaning that we go from left to right and top to bottom. Okay, and that process of looking at the image through this filter is called as convolution. Okay, so convolve the filter, meaning someone is on, someone should go mute, please. So convolve the filter with the image, meaning take the filter all across the image, meaning you do the sliding window operation that if you have heard of. So it is a sliding window operation concept. You slide the filter from left to right and top to bottom, and at every position you do the computation. What computation? So what is happening here is you are connecting, there are, I mean, 5 by 5 into 3 means 25 into 3, 75 neurons. Here it will focus on to those 75 neurons of this patch. So there will be connections for every neuron. These 75 neurons are connected, and it will try to perform the same summation and squashing. Okay, so convolution is apply this filter on the image, move it across from left to right, top to bottom, and at every position do the same dot product computation followed by um, what do you say, the squashing function or the activation function. See here, this patch applied onto this region of the image will give you one number because it is connected to one neuron. With respect to one neuron, it generates one number because of your dot product computation. So assume this W is the parameters of this filter. Okay, X is the pix pixels corresponding to the region where the filter is present at this moment. So you do the dot product computation, which leads to one value, and in the process we add in one more parameter called as bias. Bias is just to adjust the activation. Okay, so you just forget it as of now, only the dot product, it is just one scalar that is added up, right? So 75 dimensional dot product will happen, plus one bias will come out. This will be one number. Then you pass this number to the activation function that will take it to a specific scale, as we have understood before. Now, if you move this 5 by 5 filter all across this 32 by 32 image, then you will end up seeing a 28 by 28 matrix. Because if it is present here at this top left position, it will generate one value. Keep it here in 1 comma 1. Then move the filter. Okay, move the filter at just one column right. Then you will have one more value generated. Place it in the 1 comma 2 location. Then move it one column right, one column right. Likewise, till where you can move? You can move till the 27th column, because if you go to 28th column, 28 plus 5 will become 33. So it will go above, it'll just exclude. I mean, you cannot apply the filter after 32. So the last column that this filter gets placed is at the 27th. So 0 to 27 becomes totally 28 columns. And similarly, top to bottom also, it will go up to the row 27. So if you place your filter here at 27, so 27 plus 5 is 32. So it will get placed at this location, and you generate one value. So that is how you can just push those each values that are generated when you do the convolution process onto a matrix. Okay, but now this is only one value that is computed, even though you have three here, but after the dot product you get only one value. But the feature the matrix size of such values placed in a respective position will become 28 by 28 for this 32 by 32 image. Now this you can call it as one feature map or activation map. Okay, so meaning that it has done some feature extraction. This is the output of that feature extraction. If you visualize this, you will see what the features that are extracted. In the initial layers you won't see such prominent visualization of it, but if you take this feature map and take it as input to the next layer, so what goes to the next layer as input? This feature map. This becomes a input to the next layer that does the computation again by passing one more kernel on top of this and computing new feature map. So that feature map may be some more effective in terms of visualization. So it may be learning simple pixel combination here. The next feature map maybe is a combination of pixel combinations, maybe called as edges, then the edge combinations. That is how, if you go deeper, you will see a lot of higher level abstracted features that are extracted. Okay. So as I said, I want to use multiple filters just to make sure that I am trying to look at the image from different perspectives. So if you use, say for example, 6 filters of 5 by 5 size onto this image and do the convolution, each filter will generate one feature map of size 28 by 28, and hence totally 6 filters generate 6 feature maps. Stack them again to form one 3D block of size 28 by 28 into 6. Now your input image of size 32 by 32 by 3 channel is converted into a feature map, or again you can call it as, basically I say this as feature, this also has a feature map at one layer. This is a feature map at a next layer. So feature map in the current layer is 32 by 32 cross 3. Now it is changed to 28 by 28 cross 6. There are 6 channels. Okay. So this is the convolution process, and you just go on stacking them. So do the convolution, and what you understood in the convolution is each filter will be convolved, and in each filter placement you do the dot product computation and an activation function. So the activation function can be anything like what we've discussed, the sigmoid, and there is a tan hyperbolic is also there, and the mostly used and well-known feature, the activation function today, even today, is ReLU or its variants, which is rectified linear unit, which is a very simple activation. It is 0 comma max. So if the input to that function is less than 0, it converts it to 0. If the input is more than 0, it passes it as it is. So it's a simple nonlinear function like this. Okay, you can study it in detail. So that activation function is used, and I keep 6 filters. So the output becomes 28 by 28 cross 6 in the first layer. And if I push this as input to the next layer, keeping 10 filters and each filter of size 5 by 5, and this 6 will be decided based on the number of channels that you are previous feature map has. See here it is 3 and it is 6 here, and once you process this it generates 10 uh, channels, because you are keeping 10 filters or the 10 uh, kernels for the processing. Subsequently you just go on and on. You can keep several such convolution layers stacked up to form a deep convolution neural network. So what is a convolution neural network? It is just stacking. It's a neural network basically. You have input layer, output layer, and hidden layers. But the hidden layers are spatially connected through the convolution operation, and hence at each layer you do perform the convolution operation by using the filters concept, and hence it is called as a convolutional neural network. Okay, which is very much applicable for the image type of data. So if you try to imagine, and this is some visualization obtained from this article. So if you go through, you'll come to know. So when they took the image of dog and at some, and this is the VGG16, a standard architecture in the convolutional neural network, um research history. So VGG16 at the first convolution layer, the feature maps looks like this. Okay, different feature maps, and if you go to the third convolution layer, it looks like this, and in the fifth convolution layer, it is more complicated representation. So as you go deeper and deeper, the feature maps will have better and better representation of the input data. So these are lower level features, these are some middle level features, these are high level features, and at the end those high level features should be fed to a classification layer, okay, which is decided based on your number of outputs. If it's a classification problem, you keep a classification layer that I'll come to that you'll come to know in my subsequent slides. But you just know there will be at the end one layer which is responsible for using those last high level feature generated after the convolution at this level as input and generates the class labels. That's it. Okay. So this every layer is just doing the feature extraction, or you can say the data is getting represented in a best possible way so that your classifier can do its job of classifying the data. So at the end, the feature map again gets converted into a vector, and that vector will be fed into classifier. Now when I say a classifier, you can stop at this point and you can bring in your conventional classifier, meaning you can um, break the network at this point, take the outputs generated out of this layer, I mean, again, flatten them or convert them into one dimensional. Like as you see, the feature maps are three-dimensional, right? Convert them to one dimensional, because multi 28 by 28 into 6 becomes one single vector. Use that vector as a feature vector for any of your conventional machine learning techniques, like you push it as a feature vector to train your SVM. Now your SVM use that features as input features to train, or otherwise in the neural network itself you can train a classifier by keeping a classification layer as so. Okay, this is again some more activation maps. I'll show you with the demo these things. So if you try to visualize the end-to-end network, you push in the sample and stack up several convolution layers followed by some more layer, which is the, so you call the activation itself as a layer. Okay, or you combinedly you can say convolution operation has convolution plus activation together as one operation. So convolution followed by ReLU activation, again one more convolution activation. Okay, and subsampling. So this is a pooling called a subsampling layer. I'll discuss with you again. So you just stack up such several convolution layers which start from lower level features. Gradually they get transformed into very high level features, and ultimately you keep one last layer for the classification, which can be your fully connected layer. Means connect all the uh, pixels, I mean all the neurons of this last layer of convolution to all the neurons of the one more layer that you keep to make it a fully connected layer that I showed you previously. What is a fully connected layer? So if you have all the connections established between two layers, then that layer is called as fully connected layer. Now, after this fully connected layers, you keep your output expectation. So I want from the first neuron uh, to be high if it is car. So first neuron is responsible to say the input is car. Second neuron is responsible to say truck. So if the first neuron gets highly activated for some sample, okay, then that sample is treated as car, meaning that highly activated in the sense because you keep the activation something in the range of 0 to 1. So if it is close to 1, meaning this neuron is very much activated, meaning that the feature vectors and their combination are declaring that this input is a car. Sometimes when you push ship as the input, the the weights and the factors will make this neuron get highly activated, and hence you declare the class label as ship. But training is very important, so it will not happen in one go. As you understood, for a simple neural network also there will be several forward process and backward process. What I'm showing you here is the network which is well trained to decide the input. Okay, fine. So if I show you the closer look of how the convolution happens, you just see this is how it happens. If you assume a 7 cross 7 input uh, image and a simple filter of 3 cross 3, it just goes all over the image from left to right, top to bottom to generate a 5 cross 5, a 5 cross 5 output. Okay, but wait, what you also can do is instead of pushing this filter one column at a time, you can push it two column at a time or three column at a time. So what is that number of columns that you want to skip is called as stride. So by default stride is one, meaning that it moves one column at a time. As you can see, it is placed here, pushed one column, compute again, pushed one column, compute again, pushed one column. Instead, you can keep stride as two, then after first placement, the next computation will happen by skipping two columns. Similarly, two rows will be skipped. Okay. So when you keep stride as two columns and two rows will be skipped in the convolution process, and which lead to a smaller sized feature map output. So for this example, if you use 3 cross 3 filter and stride 2, the output feature map will have 3 cross 3 size. Okay. Whereas if you put 3 as the stride, now you cannot apply 3 stride because as you can see, after first step, if I move it, it will move to this box. After skipping 1, 2, 3 columns, it will come over here. Okay. Again, I cannot skip 3 columns and place my filter because I do not have 2 more extra columns. Or I have to stop at this point and leaving this column not processed. So you cannot do so, and hence stride 3 is not possible for this image size and this filter size. Okay. And if you want to make it possible, only option is you have to append this image with several other rows and columns so that this stride can be fit. So what you are lagging here, you are lagging two more columns so that this 3 cross 3 stride the filter can be placed. So add two columns. So instead of adding two columns here, add one column here, add one column here. Similarly, add one row here, add one row here. So that's called as zero. I mean, add columns and rows having values as zeros. So it's called as zero padding so that you can use any stride of your choice. So based on the stride size, you have to, I mean, the number of zero padding rows and columns will be decided. So you can now come out with a formula to decide what will be the output feature map size based on the input feature map size and the filter size and the stride that you use. So if input feature map size is n and filter size is f and stride is stride plus 1, this is the formulation. Say in our example, if n is 7, f is 3, then you had 5 as the feature map output feature map size. Similarly for stride 2 it is 3. For stride 3 it is not possible, so use this formula, decide what is the best stride you can go with and what should be your output feature map, and go with that. Okay. So as I told you, yeah, this is how you do the zero padding so that you can put the stride of your choice. Okay. For 3 stride, you have to have 1 0 padding. For 5 stride, you have to have 2 0 padding, so that there are totally 4 extra rows and columns available with the image. Okay. So coming back to the stacking up of convolution layers, this is how now it works. So now if you want to decide what will be the output volume size given the input volume and filters and the stride and padding, so this is the formula. It is uh, the input size. Okay. This is the filter size 2 into 2 2 cross 2. Okay. And 5 is the mm, sorry 5 is the filter size, padding is 2, right, and divided by 1 plus 1, so 32. So this is the formula. So the generalized formula can be obtained by using this concept. So what is the input size? Filter size 2 into the 0 padding divided by the stride plus 1. Okay. Hope that's clear. So it is a detailed version of it. So I'll share the slide across. You can go through. So as you can see, this is what is happening at H filter processing. So this one neuron gets inputs from all the connected neurons here with respect to this filter. So this filter has weights, W's. So what is filter? Filter is W's, and the corresponding image patch is X, X0, X1, X2. So do the dot product of your filter with the corresponding image patch and plus the bias, use the summation, push it to the activation function F, which can be your sigmoid function or ReLU function as I said, and hence it generates one single value for that neuron. That is called as the activation of the neuron. So this neuron will be highly activated if this filter sees a corresponding match. Meaning, if you assume a filter, like you have come across with several filters so far, if I understand right, if you are into image processing, digital image processing, you should know the different edge extraction techniques like Canny, Sobel, right? So Canny is, you have a Canny mask or you call it as Canny filter. So what it tries to look at a specific type of edge. So if there is a edge, Canny will produce high value. So you can use Canny as a filter, but I don't want to use any specific predefined filter here. Instead, I want to make sure the network learns a filter. So what is a filter? Canny filter? Basically, it is just the weights that you keep. 1 minus 2, 1, right? 1, 2, 1 kind of thing that you see in the filters. So those are the weights. And I don't want to predefine my weights. I just say the filter size. Let the weights be decided. Let the network decide what edge it wants to see, what type of edge it wants to see, at what level of the network, at what layer of the network. Okay, that is where the training will help you. So whenever it looks at a patch and sees that there is a high likely, probably if you try to imagine from the higher level of abstraction, if this patch is trying to look at a eye region, maybe down the several layers, like in the say in the 10th convolution layer, if your filter is trying to look at the eye region, and when you move the filter all across the image, I mean the filter map, the feature map or the activation map, if the filter gets placed onto the region where there is I, then the dot product value goes very high, and hence when the slashing function is applied onto that, the slashing function value becomes very close to 1, meaning that neuron gets highly activated, meaning that it has seen an eye in that place. Okay, so whenever you push in an image which is face, then eye is an important feature to declare that image as a face. So there is a filter that is trained to look at eye region. If while convolution, if it sees the eye region on the input image, the test image, then that particular neuron will get highly activated and that will percolate to the last layer, that high activation. Okay, and hence that becomes one of the deciding factors to declare that image as a face. So I'm giving you one example of a specific feature. Likewise, in a phase, there may be several such, you know, important regions, important features that will be learned by your network and will be tested when you push in an input image. So, for example, if it is a car, so the network has learned, and there is one specific layer and a neuron and a particular feature map that is trained and kept in the network during your training process to look at, say, for example, the wheel region of a image. So if there is a wheel in the input image, then it's probably says there is a chances that it is a car, but not sure if it is a car unless all the other supporting neurons and features declare that yes, the other related features are also present and their spatial positioning is matching with what is the car's spatial positioning of the wheels and the body and the other parts of it. Then only it finally declares. It's not the only one feature that it will work out. So this is how the networks will finally work out to be so much of, I mean, highly effective and generalizable. And in your convolution, you understood what the convolution is and what the activation is. But one more factor is the subsampling layer. So, this is used to just make some more reduction in the number of neurons, or just to make it less computationally effective, and at the same time to increase the kind of generalizability of your network. So this generally the image sizes will be big, and after convolution it is not so drastically reduced. So if it is 1000 by 1000, after applying a 5 cross 5 filter, it may reduce to 997 by 997. It is still very big. But if I just do a simple rescaling of this 997 into half of it, okay, then I don't find lot of information loss in my image at that scale also, right? If 997 is divided into 450, say 455 or 445, you don't see a lot of difference in terms of the information that you are having in the reduced size. So I don't want to simply do a rescaling. Instead, I want to use a subsampling layer, which reduces the, I mean, downsamples the image size from say 224 to 112 by using the concept of pooling, which is you, as if you assume this is your input, I again keep a filter. Now there is no weights that you need to train. It is just that a box, I mean a filter size is decided. If you say 2 by 2, it looks at every 2 by 2 region from left to right. At every 2 by 2 region, it does a simple computation. If you say the pooling should be max pooling, I mean the downsampling should be through max pooling, meaning this 2 by 2 region, in this 2 by 2 region you compute what is the maximum value. Why max pooling is helpful? Because this values which are maximum indicating that there is a feature of importance, right? Because your neurons get highly activated and they will have high values in the region where there is some uh, discriminative or notable feature present. So I want to keep such notable features and eliminate some unimportant features. So do the max pooling, take out 6, keep it here, and in this, and then push the filter to the next block. Do the max pooling means see what is the maximum, keep it in the output. Again here, keep it in the output. So this will now reduced into from 4 by 4, it is reduced to 2 by 2. Similarly, if it is 512 by 512, if we input feature map, after max pooling with 2 by 2 filter size, and the stride 2, as you can see, I directly moved to the third column. So stride 2, then your 512 by 512 image becomes 256 by 256 without much information loss, and at the same time keeping the generalizability. What is the generalizability is, if you are working with, say for example, face images, then chances that this is a high resolution image, and spatially if I decide to go with a specific location at which the eye region comes in, I may be doing something wrong, because in the next image that I see, the face is slightly taken to the top and the eye region might have been pushed up, or it might have been pulled down. So the object positioning in the image may slightly change depending on the how the acquisition has happened, and hence I want to accommodate to those small spatial moments in the actual real-time scenario. That is where this subsampling will also help you. So it is helping you in two senses. One is it is reducing the filter size, thereby reducing the number of computations required, meaning the number of connections will reduce. And on the other hand, it is helping you to generalize well to adapt to the moving spatial locations. Okay, right, this is the algorithmic representation of that. And coming back to the last layer, which is responsible for classification, you keep the fully connected layer, meaning there is one more hidden layer after all the stacked up convolution and pooling layers. So pooling, not necessarily, you may not require at all the, I mean, after all the convolutions, you decide after say two convolution, I want to have one pooling. Okay, after two convolution pooling, and as you go to the last, you do not want pooling. So such configurations you can decide. So it is all dependent on you how you want to stack up these layers. But general, I mean, in specific, convolution follows by ReLU, because convolution should be followed by the activation that should be there. But whether after this you want the pooling or not, you can decide that. You can directly go to another convolution and the activation followed by next the pooling or subsampling layer. But at the end, after having several convolutions, now you want to decide the class. So you keep a fully connected layer, meaning you have one hidden layer which connects all the neurons of this layer to all the neurons in the previous layer. So your last convolution layer output will get converted into a single vector, and that gets connected to all the neurons. So this is a fully connected layer. So the final layer that you keep after the fully connected layer maybe is layer with number of neurons equal to the number of classes, so that you assign one neuron to one class and you ask this neuron should be 1 and other all should be 0 when I pass in an image from class 1. That could be your expectation. Accordingly you can compute the loss, and that is how these networks are visualized in this way. So you have a image and there will be several convolution and subsampling layers, and at the end the final feature map gets converted into a uh, a flattened into one dimensional vector, and you bring in a fully connected layer, and you can decide to go for stacking up several fully connected layers again. But remember, the convolution layers will have less complexity compared to fully connected layers, because the number of connections are less compared to the number of connections between fully connected layers. Okay. Yes. I think we are close to the lunchtime. We'll break at this point. In the next session, I'll come back and show you the important neural architectures in computer vision domain, and I'll take you through some of the demonstration. Yeah, we can take some 5 minutes if you have any clarification to be made on the CNN part.
Yes, participants, you can respond if you have any queries, doubts.
Okay, so probably when we meet back again at 2:30, we can start with some clarifications if you have. Otherwise, we'll move forward with architectures. I'll show you a couple of architectures, and then we'll go to the uh, demonstration of different. I mean, a couple of examples for some use cases.
Sir,
Okay.
any tool is there for this to implement all this
Yes,
remote?
sir. We'll be using we'll be working with Python. On
Mm.
Python, we'll be using deep learning frameworks like TensorFlow, Keras, and PyTorch. So for implementation, if you have your laptops, I think setting up is difficult. And anyway, what I'll do is I'll
No,
be
no,
using.
sir. No, no need of doing parallel. You just show it. That's enough if
Yeah, I'll
possible.
be showing it,
Uh,
and
uh,
I'll be sharing the links also so that you can repeat. And anyway, I'll be doing through the Google Colab.
yes, sir. Yes.
Hence, I'll share you the notebooks also. So I'll be using Google Colab Jupyter notebooks. You can also execute in parallel with me and see how it works.
Okay, okay. Then no need
Okay.
of separate software, na? Online is
As
enough.
of now, no need. Online will directly go to Google Colab.
Okay.
Hmm?
Okay, sir. Okay.
All right, participants. Then we'll meet back again after the lunch at 2:30 sharp, and
Yes, yes.
we'll see some interesting architectures.
Okay, sir. Thank you.
Okay, thank you so much.
Thank you, participants. We'll meet again 2:30 at lunch and come back.